Right now, as you watch this, there's something moving silently through the walls around you. It has no color, no smell. You can't see it, touch it, or hear it when it's behaving normally. But it powers every device you use, every light you turn on, every piece of technology in your life. This invisible force is electricity. Everything starts at the atomic level. Atoms are made of three main parts: protons, positive charge; neutrons, no charge; electrons, negative charge. Electricity is all about electrons, the tiny, negatively charged particles that orbit around the nucleus. In some materials, like metal, electrons are loosely attached. They're free to move from atom to atom. This movement is the foundation of electricity. When electrons flow in one direction, you get electric current. When electrons build up in one place, you get static electricity. And when electrons shift due to chemical reactions, you get batteries. Electricity isn't some mysterious substance. It's simply the movement and behavior of electrons. So what exactly is electric current? It's the rate at which electrons move through a conductor, usually a metal wire. We measure current in amperes or amps. Here's something surprising. Electrons don't move fast, they drift slowly through the wire, but the electrical effect, the energy, it moves almost at the speed of light. It's like pushing a row of balls. The first ball barely moves, but the one at the end shoots out instantly. Electricity works the same way. A power source pushes electrons through the circuit, and devices tap into that flow to do work. So what pushes electrons? That push is called voltage. Voltage is electrical pressure, the force that drives electrons from one place to another. A battery creates voltage through chemical reactions. One side accumulates extra electrons, negative, and the other side loses electrons, positive. Connect them with a wire, and electrons flow from the negative side to the positive. That flow powers whatever is connected in between. Devices don't suck electricity. The voltage pushes it through. Now combine voltage and current and you get electric power. Power is measured in watts and it tells you how much work electricity can do per second. The relationship is simple. Power equals voltage times current. High voltage plus high current equals lots of power. Low voltage plus low current equals little power. A phone charger uses 5 volts and tiny current. A microwave uses 120 volts and high current. Power lines use tens of thousands of volts to move electricity efficiently across long distances. Wattage isn't just a number on your light bulb. It's how much electrical energy your device uses. Another important concept: electricity and magnetism are linked. When electrons move through a wire, they generate a magnetic field around it, and when a magnetic field moves near a wire, it generates electricity. This is electromagnetism. The reason transformers, motors, and generators exist, it's not two separate forces, it's one combined phenomenon: electromagnetic force. This relationship powers the entire modern world. Let's look at how electricity is generated. Most power plants, coal, gas, nuclear, hydro, wind, all use the same basic mechanism. A turbine spins a generator. Inside the generator, magnets rotate near coils of wire. The changing magnetic field induces electron movement. That movement becomes electric current. Power plants differ only in what spins the turbine's steam: coal, gas, nuclear; falling water, hydroelectric; wind farms, steam from heat in earth, geothermal; ocean tides, tidal power. The core process is always the same: mechanical motion, magnetic field change, electricity. There's one major exception: solar power. Solar panels convert light directly into electricity. Photons from sunlight hit electrons in silicon cells and knock them loose. The freed electrons are guided into a circuit, creating current. That's the photovoltaic effect. Solar panels produce direct current, DC, which gets converted into alternating current, AC, for homes and power grids. This brings us to the two types of electrical current. Direct current, DC, electrons flow in one direction only, used in batteries, phones, laptops, solar panels. 2. Alternating current, AC. Electrons don't move forward and backward. They vibrate rapidly, changing direction many times per second. Why use AC? Because AC is easier to transform into high or low voltages, making long distance transmission incredibly efficient. That's why power outlets use AC. It's the most practical way to move electricity across a country. The world uses DC for small electronics and AC for big power. Now let's zoom into something fundamental: circuits. A circuit is a complete loop that electrons can travel through. If the loop is broken, a switch turned off, a wire unplugged, or a fuse blown, electrons stop flowing. Every device modifies the flow of electrons. Light bulbs resist the flow and glow. Motors convert electrical energy into motion. Heaters convert it into heat. Electronics manipulate it using microchips. Electricity doesn't get used up. its energy gets converted into other forms. The electrons keep moving, just with less energy than before. But what happens when there's too much current? Wires can overheat, devices can get damaged, fire becomes a risk. That's why circuits have fuses and breakers. They automatically cut the flow if current exceeds safe levels. Electricity must be controlled. Otherwise, the same force that powers your home can be dangerous. Why is electricity dangerous to the human body? Because your nervous system runs on electrical signals. External current can disrupt those signals, cause muscle contractions, interfere with your heart's rhythm, or generate heat that damages tissue. The severity depends on current amount, path through the body, duration of contact, voltage pushing it. Electricity isn't evil. It's neutral, but it must be respected. Let's talk motors, one of the most important electrical inventions in history. Electric motors convert electrical energy into motion. Electrons flow in a coil. This creates a magnetic field. The field pushes against magnets, the rotor spins. That same principle powers fans, washing machines, cars, factory machines, hard drives, elevators. Electric motors are everywhere. They're the heart of the modern mechanical world. Another common use, lighting. Traditional bulbs heat a thin wire until it glows. LEDs use semiconductors that emit light when electrons jump energy levels. LEDs are vastly more efficient because energy becomes light, not heat. Electricity isn't just movement, it's transformation. In electronics, electricity becomes information. Microchips control the flow of electrons through tiny pathways called transistors. A transistor can block or allow flow. Like a microscopic switch, billions of these switches arranged on a chip allow computers to calculate, store data, process signals, run software, display graphics. Modern technology is built on the precise control of electron flow. Now, let's zoom out to the biggest scale, the electrical grid. The grid moves electricity from power plants to homes and businesses. It has three major steps: generation, power plants create electricity; transmission, high voltage lines move it long distances; distribution, substations reduce voltage and deliver it to homes. Electricity must be generated exactly as fast as it's used. You can't store large amounts easily yet, so the grid constantly balances supply and demand every second. This coordination is what keeps your lights on. But storage is improving. Modern batteries store electrical energy using chemical reactions. Lithium ions move between electrodes, carrying charge. Energy storage is crucial for renewable energy because wind and sunlight aren't constant. Batteries help stabilize the grid. Electricity plus storage equals the future of energy. Nature also creates electricity. Lightning is a massive discharge of static electricity. Inside clouds, ice particles rub together, separating charges. The bottom of the cloud becomes negatively charged, the ground becomes positively charged. When the voltage becomes high enough, air breaks down and a bolt of electricity equalizes the charges. Lightning is electricity released on a massive scale. The same process as static shock, but millions of times stronger. So, what is electricity, really? It's the behavior of electrons. It's current, electrons moving. It's voltage, pressure pushing electrons. It's power, energy converted into work. It's magnetism, linked to every electric flow. It's the force that spins turbines, runs computers, lights cities, and powers civilization. Electricity is not mysterious. It's the most flexible, controllable form of energy we have, and the foundation of the modern world.